Awesome.
Are you okay with us recording this, Melissa?
Yeah, of course. Yeah, of course.
All right. We have said that yeah, you can change your mind at the end if you want.
Okay.
All right. And
I had
let's see. Okay. All right. So thank you all for being here. Okay. Langston, thank you. Hi, Josh. All right. Let's see. So today's speaker is, I'm excited to have here. She's probably the most recent graduate who's done this. She graduated in 2019.
Yes. Yeah.
Yeah. Okay.
Yeah.
And actually, I still remember your freshman year. The physics class was in Fitzell in one of those terrace stadiums. That was a beautiful room.
Yeah, we were down in Bugby for labs.
For labs, that was not so good. But
Yeah.
So Melissa majored in physics here. She majored in math here, but she also took every engineering course she could get her hands on too along the way. And then I think what I find most interesting is that her interests were an area of engineering that I know not a lot about, but seems like it has tremendous opportunity, particularly as our society faces challenges going forward. And so she's now a graduate student at the University of New Hampshire. She's we've actually got a little tradition of graduate students there now. One of our previous speakers was a grad student there, and Nathan Rutherford is there. UNH has become one of my favorite places to go because they have cool facilities, particularly I think in the geophysics space sciences realm. Anyway, that's enough of me. You good?
Yeah, I think so.
Okay.
Okay, cool. And thank you for the introduction. So as you already said, I'm a PhD student in ocean engineering at the University of New Hampshire. So I'm going to talk to you a little bit about that today and some other things. So just to give you an outline of what I'm going to talk about, I'm going to go through an introduction about me type of origin story deal. And then I'm going to connect Oneonta to now, where I am now. So how that prepared me for now, talk about ocean engineering in general, as well as my current research project, and give you some insight into trials and tribulations that I personally faced, as well as some advice and takeaways. So hopefully you get something out of this instead of me just rambling on. But with that, so a little bit about me. I'm from Long Beach, New York originally, which is on Long Island, as I've shown you in the map. And I grew up 5 houses from the beach, as you can see in the bottom picture. So it's something that I had in my life a lot, especially in the fun side of things and my breaks and things. But as you'll see, I ended up connecting it to a career, which is definitely something I'm happy about. But now my time in Oneonta, as mentioned, I attended from 2015 to 2019. That's when I graduated. As you can see by the little red circle, this is the line of physics majors that graduated with me. You'll see some of the familiar faces, at least the professors anyway. I made some great friends. I met my current boyfriend, Nathan Rutherford. I don't think dabbing is probably cool anymore, but at the time it was maybe semi-cool, probably not. But that was something I took from there. I was a physics and math major, as you mentioned, spent a lot of time in physical science. I loved when they built that building. It was really nice. And then I also was on the women's lacrosse team at the same time, which was another great experience at Oneonta that I very much enjoyed. I also worked as a tutor in the Student Learning Center for 3 years, specifically for calculus, actually, which I very much enjoyed teaching and helping students with that. And then I also was an orientation leader for 2 years, which was another really cool experience if you had the opportunity. I got to meet people from all over campus that I wouldn't have met otherwise. And other than that, I was involved in research. So I did math research with Laura Montiano, specifically looking at hyperbolic geometry for about 3 years. And then I also did research with Gallagher, as he mentioned a little bit. So I just put this picture of Niagara Falls because I actually presented at a conference in Canada with the math department, which was really cool because I got to see Niagara Falls, as well as some of the other conferences locally that I presented at. And as you can see here. So that's just a little bit about me, specifically in terms of Oneonta. And then thinking back on this, how did I get from all of that to a graduate student in ocean engineering at UNH? So that's kind of what I wanted to discuss first. So we kind of have to go back a little bit in time. So in October 2012, Hurricane Sandy affected the Northeast. I'm sure some of you remember that. And my town, as I mentioned, living right on the beach, was severely impacted. As you can see, the water line or the sand line, that's where how much the water came into my town. I was up to about a waist high of water in my house, in my first floor at the time, as well as the boardwalk was destroyed, and we had sand all over the streets. As you can see in this picture here, covered cars, some of the cars were tossed, they looked like toys almost the next day by some of the sand. And this bottom picture is a New Jersey picture, but you can see again some of the devastation. So this happened, like I said, 2012. I was a sophomore in high school, and it was something that happened. It really stunk. I was out of power for a while, and I was out of my home for a while and things like that. But it's not something I super thought about as I went to college at the time. But then a couple of years later, so in the summer of 2018, which is when the summer before my senior year of college, the U.S. Army Corps of Engineers started this giant coastal resiliency storm prevention project in my hometown. As you can see here, they input a pipe along the entire beach, and they actually pulled sand from out in the ocean to make the coastline longer. So to extend the distance from the water to the houses, in order to prevent flooding or take a more longer for flooding to happen, I guess, so to speak. This little umbrella here, I think is my dad actually. For whatever reason, it was windy. He decided to set up right next to the pipe, which was how close they let civilians get to a lot of this stuff, as you'll see in some of the pictures. And then over here on the right is actually that pumping that I was talking about. It's termed dredging usually is what it's called. And I zoomed in on a little bit here. So it looks like a mound of sand, but it's actually sand from out in the ocean being pumped through the pipe and onto the beach. And you can see with the water too, that it brings water with it as well as there was this big machine that was just overseeing a lot of this. And then just to show you how they then move that sand around and extend the beach out with basically little bulldozers. And the sand that came out from the middle of the ocean now looks like this, or at least right after it happened, which is a big change from the white, sandy, soft beach. It was dark, it was almost purple in color and very grainy. As you can see here again, civilians were very close to a lot of this, which I thought was funny that they let that happen. But it's something I watched that summer that I then became more curious about. And here's another picture of that dredging happening from the actual Army Corps of Engineers on my town. So you can see the sand actually coming out of the pipe, as well as this is a different project, not the Long Beach project, but I wanted to show you again how they can extend it, at least from like an overview perspective. So again, watching all of this happen, I thought this is crazy and someone had to be in charge of this. And at the time I was interested in engineering in a general sense, but I wasn't sure exactly which direction or didn't know if I had the experience to go anywhere. And this was something that I was like, this is something I can do. So I began to look a little bit more into that. And just another couple quick other things they did. They rebuilt the dunes along the boardwalk. Those were destroyed in the storm. They put all big new ones in. They redid the jetties. That was another big project, as well as just houses in general was lifted. So this is my house from home when it was actually lifted 3 stories up at the time. There's my dad again. But at the time, that was something also that happened around that same summer. And again, so I became more interested and I wanted to know more about it as I then went to Oneonta for my senior year. So that's where I'm going to start to give you some connections after we've done the backstory a little bit about how that prepared me to now, because seeing that in my hometown actually interested me in ocean engineering. That's what I began to look up and see. But at the same time, Oneonta actually prepared me for what I would experience when I eventually got to grad school. So that's what I wanted to talk about quickly now. So one major thing is the math and physics knowledge, which sounds kind of corny considering that's what you spend a lot of time doing in undergrad is classes and learning. But stepping into an engineering space with a math and physics knowledge or strength in that is not always the case. So it was something that was a good positive that I had, or a good attribute that I had in this case. And these equations are one of the first things I was assigned to do in my research in grad school, which was kind of intimidating, but at the same time, I had taken this was something I had to integrate 3 times. And I was like, I can do that. I've done that before. So that's something that you don't think about using, but it does come up. And then another example with that in terms of classes was the electronics class that Mike Fox taught at the time when I was there. So this picture on the left is actually from that class. And the pictures on the right are the stuff I do now with electronics. At the time when I took this class, to be, I guess, sort of candid with you, I hated it. I didn't think it was relevant. I was like, I am never going to use this. I do not want to do anything with electrical engineering. And and why do I have to do this class basically at the time. Not that I ever told him that or anybody that, but that was my internal dialogue, I guess. And now now where I am now, I use it all the time, even go beyond what the class taught me. So again, having a basis in that or having seen it before really helped me where I am now, at least not to be totally lost. I still learned a lot on it now, but it's something that you don't think about. Another thing in Oneonta was experience with programs. So I used MATLAB, SolidWorks, as well as Overleaf and LaTeX in my time as an undergrad, which is stuff I use almost every day now. So again, I took an engineering course there. That was a 3D design course where we looked at SolidWorks, which is where you can build models. And this was my final project here at Oneonta, actually, this picture. And again, it was something I thought was fun, kind of cool. That's something different, but I didn't think that I didn't know I would use it again. And now I actually use the same program, and now my designs are actually being printed and made in real life, which is not something that happened at Oneonta, but it's crazy to think about now. But learning that first at Oneonta helped me to, again, be able to use that now. Similarly with MATLAB, I saw that the first time with research with Gallagher, and as something that I didn't totally understand, and now I use it almost every day. So being exposed to it first, I think definitely helped. And similarly with Overleaf or LaTeX, we had to write my lab reports in advanced lab in that, which is, if anyone who doesn't know, it's kind of like it's a writing program, but it's based in coding versus a Word or a Microsoft program. And at the time, again, I was like, why do I have to use this? I can just use Word. But now as a graduate student, all your scientific papers, all of your dissertation at the end of all of this is going to be written in that type of format. So being exposed to it in the beginning or early on was definitely helpful. Another thing is just scheduling, which I feel like I'm sure you've probably all heard before in terms of going from high school to college, where now you have more free time and things like that. But in undergrad, you do have 4 or 5 classes, as well as study things or clubs or sports or whatever, or a job or whatever you might have. So your schedule is kind of packed. Versus in grad school, it gets even more free time than that. So you'll see at the bottom here, this is my schedule from last week. I have 2 meetings and I have a class and I have a seminar. Other than that, the rest of the time is mine. I have lots to do, but I still have to work on scheduling my tasks and my work in a way that's productive. So I think you do get a basis of that in undergrad that you may not think you do, but it helps when you are in a place where you have to make your own schedule. And the last thing is just undergraduate research. So like I mentioned, I did math and physics research, which are things that just help you, I think, gain experience in the sense that there's no textbook, there's no right answer. You have to learn how to ask questions and things like that, which you do in a research setting as a graduate student as well. So I think that's something very important, as well as I'm very grateful in my time at Oneonta that Gallagher at the time saw my interest and then let me help him or worked on research together that was interrelated to ocean engineering, sort of, at least in a basic sense. So I think that's something, if you're looking into doing undergraduate research, the people at Oneonta, being such a small, close-knit community the way it is, can help you with that. So if there's something you're interested in, I think you should reach out to professors and they'll help you find something that's related to your interest to do, at least semi. So I think those are kind of the big main things. I could probably talk about more things that Oneonta helped prepare me for now, but those are kind of the main ones I wanted to get out. And I hope as you're going through classes and learning things now, that you think about it a little bit too, for whatever your future entails. So now that I kind of went back a little bit, I'm going to go back to now and talk about what ocean engineering is in general. So it's kind of a broad discipline in general, as kind of Hugh mentioned in the intro. So I kind of broke it down into my own definition right now. So it's basically, I like to think about the ocean as being in the center, as you can see here. And then you take the hard sciences like math and physics, and sometimes biology less so, but it is related, and put that in the context of the ocean. And then similarly, you take other more technical degrees like electrical engineering, mechanical engineering, and oceanography, which is kind of obvious, and put those again in the context of the ocean. And there's lots of other disciplines that can fall under this too as well, like environmental engineering. A lot of them are cross disciplines, and a lot of the people that come to at least the graduate school level come from lots of different backgrounds as well. So that's kind of the way I like to think about it. But that's what makes it fun to me, that you get to take all these different things and apply it to a real life thing in the ocean, which most people have known or been to. So I think that's cool. And then just to talk a little bit about the different areas that you can work in this type of field. Just listed a bunch up top. The one I'm mostly interested in is sediment transport, which you see at the top left, or coastal processes is another way it's sometimes said, or coastal resiliency is really at the main core of the things that I want to do currently, as you can probably tell from my background. But there's lots of things you can do. You can do ocean exploration with marine robotics, where people design robots that go and explore the bottom of the ocean, as well as look at things like marine renewable energy. I have really close friends here that look at turbines. So they use tidal turbines, or they're testing tidal turbines. So it's basically putting a wind turbine into the ocean and getting the energy from the ocean. So again, that same similar background of maybe a mechanical engineer who does wind turbines is now in the ocean, as well as things like aquaculture, and some people do acoustics or ocean mapping, or one other thing is air-sea interaction, which is just looking at like weather and hurricanes in that sense, as well as things like marine structures. Like if you're going to look at an offshore drilling site, not something I'm super interested in or approving, the offshore drilling of oil, but it is something that people can work on in this type of career. And I'm probably missing some, but these are kind of the main ones that I came up with or have met experience with people in. But it's definitely a very broad field. Like even microplastics is now being studied under ocean engineering, where people trace the paths of microplastics. So I've seen that recently. So a lot of that stuff is very cool, and it's definitely a fun, different place to be. I feel like I'm learning new things about what people are doing every day. But those are the main ones I wanted to hit on, in case anyone's interested. And now another way I like to think about ocean engineering is how it's actually studied. So in the day-to-day, and the two kind of main, at least experimental side of things, is either in the laboratory or in a field setting. So laboratory is it's a facility. So working at a facility away from the ocean, where you're testing things that happen in the ocean in an idealized sense. Whereas the field is actually going to the ocean and testing things there in the real environment. So they're both helpful to make discoveries and move a field forward and move science forward. But so I wanted to talk a little bit about each of those and show you a little bit of the facilities. So for the laboratory setting, specifically for UNH, we have, as you can see at this top picture, this is our wave tank. So there's a paddle at the end that drives, you can set it and it drives waves through this, down this entryway or down this canal, so to speak. And people use it to test buoys, and they test the turbines again, the tidal turbines. They will attach it here and then let those waves or the current run through it and test certain things. So again, it's an idealized sense of what waves would be like in the ocean. Similarly, we have this other tank that we call the engineering tank. It's hard to tell from this picture, but it's about 25 feet deep, actually. Maybe a little bit more than that, actually. So people use that to test acoustic instruments, or just to run certain, to calibrate things and things of that nature, as well as the scuba class uses it to practice. So it's another widely used, another one I could just thought of off the top of my head is remotely operated vehicles. They drive those around this tank to how they would drive them in the ocean. And then the newest facility that we have is a environmental flumes tunnel. So it's a long tunnel next to the wave tank that has sand in it. And you can use a 2-piston system to actually drive waves and or currents through, and you can see what the sand is doing. So I have a lab mate working on that, and that's pretty interesting as well. And then on the field side of things, I pulled out a quick couple examples. You can work on a boat. So at the top, this is from UNH. I don't know any of those people. I think it's an old photo based on the clothes, but people go out and work on ships for weeks, 2 weeks, 3 weeks at a time and take data, which is pretty cool. Whether that's ocean mapping, or sometimes they're taking samples of the water column and looking at organisms or things of that nature. So that's something you could do as field work. And then as well as, this is a facility that UNH has where you can actually test tidal turbines. So right here is the turbine, and they can go and actually hook up real turbines and test it in the actual ocean and see how much energy they can produce. It's actually hooked up to a grid. I believe that's very ongoing work at UNH. That's very popular. It's the renewable energy side of things at my university. And then the other thing is like the beach, like I said. So this is a coastal processes experiment that I was involved in. It wasn't for my research, it was for classmates' research, but I am there helping out. I'm the short one, you can see. I don't know if I'm really that short compared to those people, or if I'm in a hole, but we spent a good 4 hours out at the beach putting these pipes in with instruments on them. So which means I got to spend the whole day swimming, basically, which is fun. So that's just another, giving you a little bit of an idea of what kind of environments you can work in if you go into this field. And now I also just wanted to give you kind of an overview of a typical day for a graduate student. So my plan wasn't graduate school in the beginning when I was an undergrad. I didn't really know too much of what to expect. So I thought giving you guys an idea of that could be helpful if anyone's interested in graduate school or just in general. Because to me, it was like, what do you do all day? Do you just take classes? Do you just do, I don't know, what do you do? So I kind of just picked out some tasks that you might do during a typical day. So some of that is classes and coursework, as I mentioned. Specifically, when you're starting your graduate school career, you're taking more classes and you're doing less research. And then as you move on, finish up the classes and you do more research and less classes. So I'm finishing up my classes now this semester, and I'll then just be doing research and my dissertation from then on, which is exciting. But other things that you do besides that would be TA responsibilities, or teaching assistant responsibilities. So usually when you go to grad school, at least for 1 year, you're required to do a TA position. And that can look like different things. Sometimes that's actually teaching a full class, or it's teaching a lab class. I taught actually a SolidWorks lab, which was, again, I came right out of undergrad knowing SolidWorks and was able to teach that. As well as you have to then grade for those labs or classes or whatever it is. So that's something you would then do during the day. Another thing is meetings, which sounds kind of lame, but I have at least 2 meetings a week where I meet with my lab group. So all the people underneath my research advisor, we all meet as a group. And then I have a one-on-one meeting where I meet with my advisor and show her what I've been working on. And then you can have other types of meetings for other responsibilities you might have, or if there's other groups that you're involved in terms of experiments. So that's something that you would also have to do. Another thing, and then is just research work, which looks like a lot of different things for lots of different people. And it's pretty standard, I think, for most graduate school fields, not just ocean engineering, but you do things like data analysis, you do things like design work, if that's your field. You do things like reading literature, so reading scientific paper, or making presentations to present your work, or working on scientific writing, as well as the experiments. So those are just a couple things that I jotted down that I thought would be helpful, and things that I do during the day. So the days do look different. It's a lot of different things, but that's what kind of makes it fun as well. It's not necessarily the same thing every day. So now to get a little more specific, I'm going to go into my research project currently. So as I mentioned, I'm interested in sediment transport as a whole, as well as coastal resiliency as the kind of driving factor behind that. So I'm looking at a process known as momentary liquefaction, or liquefaction for short. And that occurs when the sediment or soil particles lose contact with each other, and the whole solid begins to act like a fluid, as you can see in this video that'll replay here as well. And it's caused by repetitive forcing. So lots of times that's from earthquakes or ocean waves, or a combination of both, like tsunamis. So it's basically that repeated forcing of shaking the sand actually causes the water to kind of bubble up, and it begins to act like a fluid. And this has dangerous consequences. As you can see, even in this little example here, the weight sinks drastically once it's shaken like that, as well as the light ping pong ball comes to the surface. So in a real environment, that could be an earthquake that then causes a whole building to sink, or it could be the ocean waves or tsunami waves causing the pipelines of oil to be brought to the surface, which is dangerous and has very consequences in terms of money, as well as terms of the safety of people. So this is something I wanted to look more into, and it's not something that's well understood, specifically in the marine science as well as field setting. So it's studied a lot in laboratories, but not necessarily in the field. And I wanted to work in the field, actually in the ocean. So that's something that I then had to figure out, how do we measure this? How do we test this? Another way I'd like to explain this is if you've ever actually been to the beach and you stood on the edge of the shoreline and like tapped your feet repeatedly and your feet sink, that's liquefaction, at least in a local sense there. So that's what I am trying to look into now. So to do that, to measure that, I designed a instrument that we call the pressure stick, just because it's kind of basic, but it's a fully autonomous instrument that can resolve vertical pressure gradients. So there's 8 pressure temperature sensors spread out along the length of this pipe, and they spread about 70 centimeters or so, and they can sample at approximately 18 hertz, which is pretty fast, as well as that's fast enough to resolve forcing of waves. So if your sampling rate, or how many times it takes a measurement, is too long, you would miss the individual waves. So that's just an important note there. So I helped design this, as well as design circuitry for it, and put the whole thing together. So this is kind of just a drawing of it over here. You can see a zoom in on the circuit, which I showed earlier, as well as a zoom in on the pressure sensors. So we actually pot the pressure sensors in just a regular screw, so we can take them in and out of this, as you can see here. And here's another picture of it. And when I say it's fully autonomous, that just means it has all the batteries and stuff enclosed, so it doesn't have to be connected to external power, which is something that's important when you're working in the beach or in the ocean. Another thing that we have to watch working in this kind of environment is everything has to be sealed and waterproof, because if you have any leaks, you now have electronics and ocean water, which is obviously something we don't want. So that's something that has been really fun to work on. And then I now take this and use experiments with it and try and get at what that vertical pressure gradient is doing, to try and see if there is liquefaction at the end of the day. So now I'm going to take you through just some experiments that have been involved in, mostly just to show you pictures of cool things, I guess you'd say, and tell you some little stories from those, if that's okay with you guys. So the first time this instrument was successfully deployed was in the fall of 2020. So that was my first, that was my beginning of my second year of graduate school. So just coming off the COVID, so we were COVID, I guess, the start of COVID, I should say. So we did have to wear masks, which is definitely not so fun in the ocean. The rules have relaxed now that we don't have to outside, but at the time we did. And you'll note here is that pressure stick that I showed you, and it's deployed here in the ocean water. And there's my lab group again at the time, and my advisors here taking a selfie to begin with. And then we can put out other instruments with this as well, as you can see by these other pipes in the picture at the top, whereas this is the pressure stick. So from this experiment, we used a similar process as I talked about in the beginning, where they extended the beach to get this pipe into the sand and stay there. As you see this white pole here, we call it jetting, which is basically, it's a fire hose that then we pump water through, and the water, you stick it into the sand and it makes the bed fluidized, which then you can push a steel pipe down farther in, so to speak. So this takes a lot, it takes a lot of manpower. But we then came up with a quicker way to do it, which you'll see in the next slide. In the winter of 2021, we actually now use a giant drill to drill into the sand and do a similar process and able to push it down. So here's me pushing my instrument into the sand, and you'll see that it's much quicker to do. You only need 2 people versus the previous method we needed 4, which now makes this instrument and experiments kind of easy to go on the fly. So we have now almost, it could take us, we can know the day before and we can go out and put this thing out, which comes into play this coming fall, as you'll see what we did there. And here's just another picture of it, of the pressure stick again, as well as another instrument that it was put out with, which I'm not going to go into what that is, but if you have questions, I can. And another thing that's interesting that I didn't really mention about New Hampshire beaches is the tidal range. So this is low tide right now, but at high tide, it actually covers all the way up to the houses almost, and this will be completely submerged in water. So that's something that's not really common in New York beaches or any other beaches that are south of New York, but as you go more north along the East Coast, this tidal range gets even bigger. So even Canada, it's even bigger than it is here. So it can go from all the way here, like I said, to the houses, which is kind of cool, a place to work, because you can put, at low tide, we can put things out, and then by high tide, they're covered in water. But it also means that we're scheduled in that way that I have to go at low tide. So as I mentioned earlier with scheduling your day, that's when my working in field experiment time is when my schedule is very, I have to go anytime. So there are times when low tide is 5 a.m., which means I have to be at the beach at 5 a.m. And things like that, especially in the winter when it gets dark around 4. If the second low tide of the day is around 7 p.m. and it's dark, then we have to go during the first low tide, which could possibly be 5, 6 a.m., which means I have to be at the beach at 6 a.m., not necessarily getting up at 6 a.m. So it's definitely fun, but it can be tiring to do these experiments when we're actually in them. But the next one I wanted to tell you about was this past fall of 2021. Specifically, I noted as the storm season. So as I mentioned, we came up with that new, quicker way to put this in the sand, which then meant we can now basically chase storms. So whenever there would be a prediction of a big storm, we would be like, okay, we'll be ready for it. So we would go down the day before the storm hit and we would put this in, which is definitely fun, a little bit dangerous at times, or not dangerous, but a little bit scary, as you can see from this top photo. I was not allowed in the water this day. That's my roommate actually up there, my lab mate, he's about a foot taller than me, maybe a little bit more. But as you can see, he's 6 something. You can't tell how tall I am now because I'm sitting, but in this picture, you can kind of see that I'm on the shorter side. I'm 5'2" on a good day. But this day I was not allowed in the water, which is something that originally I was annoyed about, but as you can see, it's already going over his head, which means I would be, drowning. So it's not something that we play around with as well. We're very safe about what we do these things, but it does make it interesting to work with. And we thought that storms would increase the likelihood of the liquefaction, as I mentioned. And as you may know, with the environment changing and more storms and bigger storms, then that would have even more dangerous consequences if we're getting more liquefaction. And as you can see here, there was a lot going on with this storm. This was when it was buried before the storm, and you can see that orange tape, and this was after the storm. So it almost exposed a good, I don't know, 30 maybe even 50 centimeters or so, which is a lot. And usually it doesn't really change that much in previous experiments. Another quick kind of side story about this is this other small instrument that you saw before is free moving. So it actually, we lost it, so to speak. So it rolls around by itself. And we lost it that one day, or we couldn't find it when we went back because it had broken. We have a small fishing line that runs from the pressure stick to this instrument, and it broke. It snapped in half, which meant we then had to go back down that night at like 9:30 We weren't allowed to go in the water, but we went down with metal detectors to try and find it. And we did end up finding it, as you can see here with this picture where we look kind of like miners. But it was almost 9:30, 10 at night that 3 or 4 of us went down there trying to find it. We weren't allowed to go in the water again because it's nighttime, but we did search the beach and we were able to find it, which is good because that's his thesis project is on that instrument, and it's not something you want to lose because we don't really have backup because, again, we make all these instruments ourselves. So just to give you, again, I don't want to go too far into this. I'm sorry if I'm rambling, and I don't want to go too far over anyone's head, but I wanted to show you what it looks like when you get data from this instrument. So here is just a record of pressure, and it's colored by the sensors. So sensors 1 through 4 are in the water column, and sensors 5 through 8 are the ones actually in the sand. And you might be confused at why the ones in the sand have higher pressure values, but that's because they actually have more water over them because they're lower in the sand, which can sometimes be counterintuitive to think about it first. But this top sensor closest to the waves is seeing less water because there's less water above it. That's not always obvious, but. And then what I've been doing in my research is in the literature, there's an equation for liquefaction. So this is a critical pressure gradient, vertical pressure gradient, in order for liquefaction to occur. So I take this equation and I calculate the vertical pressure gradient from the data, and I compare it to the critical value that you can get from this equation using different properties of the sediment. And then I compare it to that critical value, and if it passes, that's when I think liquefaction is happening. That's what we can conclude. So that's what I'm showing in this bottom plot. And again, only looking at the sensors in the sand because the ones in the water, it doesn't make sense to use this equation because they're not in sand. They wouldn't be liquefied, so to speak. They're already in liquid. So that's what these red spikes that you see are passing of the criteria, which we can conclude then that that's when liquefaction is happening. So I hope, again, that wasn't too much or I went too quickly, but I wanted to show you a little bit of what the data processing is like as a graduate student, as well as I think it's cool. So that's kind of it for my current research project to talk about, at least today. I then wanted to go through a quick slide about trials and tribulations of a graduate student. For me personally, so this is from personal experience. I'm sure everyone has different experiences, but one thing that was difficult for me was not coming from an engineering technical background. I said that the math and physics knowledge definitely gave me an edge over some things, especially in the classroom, but not coming from a real big engineering background sometimes was hard for me, especially when I felt like I didn't know things or things like that, or I wasn't supposed to be here. And this kind of fits into my next trial was Imposter Syndrome, which is something where it's a common thing that happens with people. I don't know what it's technically called, I guess a symptom or a mental thing where you think that you're not supposed to be where you are. So you're thinking, well, at least the way I thought of it was like, I shouldn't be here, and that this is someone's joking, and someone's going to turn around one day and realize that this girl is not an engineer and she should not be here. And that was something that I struggled with, again, coming off of the similar ideas of not coming from an engineering technical background, thinking like I don't deserve to be here, which is not necessarily the case, which is not the case at the end of the day, as you can see. But especially in the beginning, it was something I struggled with in that sense. As well as being in a male-dominated field, which is something I've always been in with math and physics, but I hadn't really thought about it until I was in grad school when I actually had a female advisor and female lab mates. And I don't want to get too involved in this, but it is different when you do see people that are like you in where you spend your time. So it definitely, something I didn't realize I was missing in Oneonta, because I loved everyone in Oneonta and my experiences in the community there, and I think everyone was great, but it was something that when I had the option to not have it, or when I had the experience without it, it was something that I felt was meaningful to me. And even now, there are still some times where I am talked over because I think because I am a female sometimes, I am sometimes the only female at the field site, which is okay with me. I don't mind it. I'm used to it. I think I get along better with males, but there's one PI who will consistently talk over me or defer to my lab mate who's a guy over me, even though I've done more work on the project and things like that. So it's something that I think is common for women in this field, and I don't want to labor it, but it's something that I did have to work through, as well as the idea that everyone has a different timeline. So as you go on after undergrad, everyone's in a different time of their life, and sometimes that can be hard. As a graduate student, I had friends that went into real careers, and so I'm still in the finals week, and people are like have real jobs and talking about vacation time and things like that. So sometimes that was hard for me, as well as people coming to grad school at a different timeline as well. and as well as comparing your project or when your thesis should be done to other people. So that's something that I struggled with a bit too, the comparing, but that's something that, again, you have to work through, I think. And then the switch to remote, which I'm sure all of you have dealt with, and it's another thing I don't want to really belabor, but it did happen in my graduate school. I did go to remote classes, and now conferences are remote mostly, which is kind of a bummer. Like, I got into a conference that was supposed to be in Hawaii this past March, which would have been really fun to go to Hawaii on the school's money, but it was made remote, and I presented from New Hampshire on Zoom again. So it's definitely something that's different, and I'm trying to take it in stride with that, because again, even though I went to a remote conference, I tried to go to everything, even though everything that is possible. So positives and negatives to everything, but those are some of the things that I thought of that I had to work through. Specifically in the beginning, I'm better about most of them now, but like anything, you have good and bad days. So with that, I just wanted to wrap up quickly with advice and takeaways from some of that stuff that I kind of spoke about originally. Do something that matters to you and find what you love. So being in this field now, this matters to me, protecting the ocean, working in the ocean, thinking about the ocean, that matters to me. And I think being able to combine something else I love, math and physics, to that is really great. And I think everyone can find something like that, hopefully. And I also think it's okay to experiment with what you love. So you might think you love something originally, and I think it's okay to change that as you learn more and see more. The other thing I want to talk about is your unique experiences and talents are important. So like I said, I struggled a little bit with the imposter syndrome, but I think my experiences as coming from a more math and physics based area makes me unique. It makes me a different person in the room when we have discussions about things. If we were all the same, it wouldn't be as fun, or we wouldn't have, I don't think we'd move as fast as we do through projects or science if people aren't different. So I think to remember that about yourself, that your experiences and your talents that you have are important to bring to the table. As well as a work-life balance, which I'm sure most of you have now, fine, but as you move into a career, whether it's grad school or another type of job, it can be hard to not work all the time, because either you like it or it's a lot of time or whatnot. But I think it's very important to take breaks and to find that life balance, because doing things not work related is also important, whether that's spending time with family or doing a hobby that you like. I think all of that's an important balance to find in yourself and find what works for you, because it's different for everybody. I still think it's important to do. As well as ask questions, be curious, because again, as I told you in the backstory, if I wasn't curious about what was happening in my own hometown, I don't think I would have gotten here, which sounds crazy to think about now, but that was from being curious and asking questions. I think that's an important thing to do in life, even when you don't feel like you know something, it's okay to ask those questions. As well as everyone has a different timeline. I said that was a struggle for me, but at the same time, I think it's important advice to remember that everyone's on a different timeline, and that's okay. And you shouldn't compare yourself to others. There's no due date for when things should be done, and things like that. So with that, I would like to wrap that up, and I'm happy to take any questions, and thanks for your attention. Hope that wasn't too long.
Oh, thank you, Melissa. I would like to express, and I'm probably speaking for people, my gratitude for how much time and effort and thought you put into this.
Thanks. I hope it wasn't too much.
Oh, no, not at all. It was spectacular. And, you know, it's great to see where you are, but also we have a lot of takeaways too. Questions?
You made that pressure stick, right, for your project. What were like some of the difficulties in designing that?
Good question. One of the things that was difficult, I think, for me was the dimensions, which sounds kind of silly, but it's easy in a SolidWorks or any program setting to like make whatever you want. But when you actually then have to order the materials to then make it, the dimensions matter. So you can say, oh, I want the pipe length to be whatever, but if the facility or the where you're purchasing everything from doesn't have that diameter pipe, so to speak, then you're kind of back to the drawing board. So I think one of the things I learned, I think for the next time, because I'm currently in the process of designing something else now. Now I've done it kind of the reverse, where I look at what the manufacturing people have, so what kind of pipe dimensions they have to begin with, and then make the design off of that, if that makes sense. So that was kind of hard to like think about, or like think about where so the top comes off, the end cap, like that has to fit exactly. which is kind of a weird thing to think about in terms of designing, at least for me.
Andrew?
So I have a question about the data that you gathered from the pressure stick.
Okay.
On the graph that you had, there was the specific table where you gathered the data from the pressure, underneath the sand.
Mhm.
Why is, for one of them, it is like concave up, and for the others, it's
And
concave
concave down. Yeah, to be honest with you, I actually don't know why that is, which is something I'm trying to figure out now. The thing that what I think is, if that makes sense. It's hard to tell, but it happens with sensors 7 and 8, which are the ones very far down on the stick, so farther down in the sand. So I think what's happening is that the liquid that's already in the sand, so the water that's already in there is going up to the top sensors, and that's coming from the bottom. Does that kind of make sense out loud?
I think.
So if you kind of remember that video where I showed you where he's shaking the sand and then the water kind of bubbles up, so to speak.
Yeah.
So that water has to come from somewhere. So I think the water is coming from the bottom and then kind of pushing up on the sand at the top. So you're getting a negative or a downward, I guess it's not a negative, but you're getting a decrease in the pressure gradient down here, whereas the pressure gradient up higher is increasing, I think. But
So
that
would
makes sense.
would that be considered like inaccurate data, or I'm not sure, like how would it affect the data like gathering itself?
I don't think it's inaccurate. Currently, I think it's just because it happens repeatedly. So this is only 2 minutes of data, but and only from one day. But I have multiple different experiments that I have data from, and they all show the similar thing. So I don't, at the moment, don't think it's an inaccuracy. To answer your question, that's what I think. But it can be, as you pointed out quite nicely, it can be hard to connect the data to necessarily what's happening physically, because at least in the field versus if you work in a lab, you can kind of see and control everything. But at the same time, I'm not at the beach when this is happening. So it's like, this is what I think, and this is what I'm basing off of values like a critical value. But at the same time, there is stuff that happens that I don't actually understand yet, hopefully. That's the idea. So did that answer your question? Kind of. That wasn't really a great answer. That was a really great answer, just to be honest. But that's what I think at the moment.
So,
Mike?
I had a question about the same graph.
Okay.
But I first wanted to say that I thought your talk was fantastic. I thought it was really, inspirational in lots of different directions, insightful and thoughtful. So thanks. So you're plotting, that's your pressure gradient versus time, right?
Yep, on the bottom.
So those dotted lines, I understood that there's like some kind of a threshold gradient. And if you go above that, you've got liquefaction, right? Why are there
Yep.
a min and a max? Why would there be a max pressure gradient? Like when it goes above the max, does that mean it no longer liquefies or something?
Okay, yes, this is something I didn't have too much time to explain. So if you see the equation that I have up top, it's dependent on the porosity of the sediment, this epsilon value. And that's something that we do not measure in the field, like in situ or in real time. So in order to get a value from this equation, I have to assume the porosity of the bed. And there are studies that have this already decided based on what kind of sand you have. So based on the size of the sand, it can predict a range of porosities that are standard. So I'm using a range of porosities. So I'm getting a minimum and maximum porosity value, which then gives me 2 different criteria or a range of criteria. Did that answer your question? Yeah. So that's something that I'm trying to still figure out now, how to measure that at the same time, and then be able to just have one value or one critical value.
So you're saying that if you took that maximum value, then for that piece of data, there was only one particular very short period of time when you would have liquefaction. But
Yep.
if you have different kind of porosity or some such, then you would have more such events.
Yes, exactly. And that's based on the expected values of the porosity from scientific papers and other studies, but not necessarily from me having a real value on this day at this time.
Cool.
So yeah, that's again, the other downside of working in the field is sometimes, but that's at least two.
So you taught SolidWorks?
Yeah, I ran the lab class. So it was a mechanical engineering class where they learned, I think it was just the intro level, so it was freshmen. And they did, the lecture was just on mechanical engineering stuff, and then their labs were just working through SolidWorks problems. So I was in charge of running those.
How was that? Were you a little intimidated at first?
At first, yes, because I had taken it at Oneonta junior year, so I really had like a year or so between when I had done it. But once I got into it, it was actually easier than I thought. It was a lot of just like monitoring, or they were all sat at computers and they would just raise their hand if they had questions and things like that.
Yeah.
So I didn't have to like teach anything, I guess I should say. It was more just like being a helper if they needed it.
Other questions?
I think Josh has a question in the chat.
Oh,
He said-
go ahead, Josh.
Do you want me to read it?
Yeah, go ahead.
Okay, he said, out of curiosity, have you ever looked into aerated sands as well? I have not. This is a quick answer. So yeah, I have not. That's cool. Thanks, Josh.
So he's all right. The instrument you've built, which has 8 pressure sensors along it. And so so what I can't quite figure out is how do they get exposed to the pressure? Is water able to go into portions of that tube, or?
No, let me go back. Not exactly. So the pressure sensors themselves are very small. They're only 3 millimeters in diameter. So if you see this little picture of down, I don't know if you can see my cursor. Down here, that little white piece, that's the sensor. So it's a membrane itself that feels the pressure change on the membrane itself. So sometimes in the data we get weird spikes that are like super quick and very fat, like back and forth. And that's actually, we think, a sand grain getting inside that membrane or on top of that membrane. So sometimes that happens, but it doesn't usually move after a little while. So that little white piece is actually on the outside of the pipe, if you can see here.
Okay, and so you've got a little shield here. Yeah, I can't. You've got a little shield outside of your. So does the pressure stick go in like a PVC pipe?
Yeah, into the sand, you mean?
So the pressure stick, it looks like it's about a 1-inch diameter. Is that true?
Yep.
And that one inch diameter goes right into the ground.
Not exactly. It does, but it takes a little bit of effort on our part.
Yep.
But yeah.
And the pressure centers are mounted on the outside of that.
Mm-hmm.
So what you were talking, protecting from the seawater was all the electronics that are inside.
Yep. So this top canister, we like to call it the brains, that has the whole circuit and the battery and all those kinds of things, the SD card, and that's all in the top. So that then runs down, those wires then run down the tube and connect here at the end. And there's a seal behind. So we have them in these, they're literally just screws. And there's behind at the end of the screws, it's hard to see. There's another seal there. So it's what we call, it's an O-ring, if you've ever heard of that term. Not to assume. Yep. So that's like right behind the edge of the screw. So right behind the threads, as well as there's one also at the top inside, potted inside of this, which is kind of hard. So we take PVC. This is a PVC screw, but we've also done it with stainless steel screws, and we just core out the center to fit the little white membrane pressure sensor and the corresponding wires. so to speak.
Nathan?
About how much data would you say you get in a certain, let's say 12-hour period? Like how many different data points, how useful would said data points be?
So it takes a sample every 0.05 seconds. I get 8 pressure values and also 8 temperature values, but I don't really do much with that. That's the 18 hertz that I mentioned earlier. So are you looking for like a number of points, or or does that answer your question? Like a number of samples?
Yeah.
I would have to do the math on that, I guess, but if you think 0.05 every 0.05 seconds, so for 1 second, you're ending up with, can I do math on the spot in front of you guys? 10 of those would be, or right, am I right? So we get for 10 seconds, let me see.
Dr. French will have it before you do.
Yeah, let me get my calculator. So if you have 10 minutes of data divided by, or 10 seconds of data divided by 0.05. So we have almost 200 points every 10 seconds. So if you want to do a 60 seconds for a minute, 0.05. So about 1,200 samples per minute. So now if you do that over, so yeah, and this generally goes out for almost a day, day and a half. Some of my longest experiments are 5 days. So that's just a lot of data points as well.
You must be filling a lot of SD cards.
Yes, yes, they go. I haven't filled one up on an experiment. We've tried. So one of the things we're trying to do is put a GoPro with them at the same time to get pictures, and those fill up really fast. We've only been able to get that to last like 2 hours, 2 to 4 hours, and then they die either from the battery or the SD cards fill.
Yeah.
But yeah, so that's something that would be cool.
Andrew's got another question.
Yeah, go ahead.
So with all those data points, what do you use to like graph it?
So MATLAB as the programming tool, is that what you're asking?
I'm just wondering, I think probably, I'm just wondering how like you said, you're getting these thousands of points. How like easy is it to transfer that data onto a graph? Like, does it take long or?
Usually not. The longest part is converting the data, I would say. So it comes in an SD card here. There's a data logger, which is where it records all the values to that it senses. And then that records it on an SD card. So I take the SD card from here and have to put that in a computer, and it comes out just as mumbled. And I have to then put it through, it's a code that came with the sensors, where you go through the command prompt of your computer, and it will convert it from there to a text file, and then you can read it and it looks normal. And then from the text file, I then have to pull it into MATLAB and do that. So normally that first conversion, if it's really long, can take on the order of minutes, 5 minutes, 10 minutes, but MATLAB is a very powerful processing tool. So it can handle all the data once it's in there, at least at the basic sense of just plotting the values. You then, as looking at the data, you then do other things to it. You can like compute spectrum and things like that, which then it can start to take longer if I'm using the entire record, which I usually don't, in terms of like, I'll plot the whole record and look at it, make sure everything's okay. But then from there, I usually pick out interesting parts or things like that. And then you're working with like you saw that figure I showed is only 2 minutes of data, and that will run quickly for most things. So sort of as a workflow that way.
Mike's got another one.
Does your brain circuit have some kind of microprocessor that you have to code?
Yep. So it's all Arduino based, actually. So the idea of these instruments that my lab does is to make them quick and like cheap to make, so to speak, as well as get them for what we actually want. But yeah, so it's a Arduino interface. So we code in Arduino. And then for this particular one, we've switched to using Teensies on the actual instruments themselves. So usually when we practice the circuit, it's Arduinos, but then this is a Teensy 4.0 microprocessor that we actually put in them.
You can put the Arduino code right onto that particular chip.
Yep, it works on them. So yeah, so it's the same interface. And then we have like a multiplexer hooked up that's how I can have so many sensors. And then the SD card, and that's pretty much, and then the battery on the back. Pretty much the gist of it.
You took circuits?
I did take circuits with you.
I know you did, but you said you didn't like it. You hated it.
I did not like it. Now I like it, but at the time I was having trouble, I guess, maybe seeing the real world applicability. And when I took circuits with you, a lot of it was the analog stuff, the like playing with the whatchamacallit, like it was more finicky than like Arduino, where it's, you know what I mean? We only got to Arduino, I think, the last 2 weeks of the class with you.
I think
At least
now
mine.
we do a lot more of that digital and Arduino stuff now.
Okay.
Now, when you were here, now we have a PCB mill, so we make our own PCBs.
You make them?
Yeah,
So
we make,
that's what I have here, but we have to send them out. I get them from a German company. Like I have to send them my designs, and
why don't you
you
email?
have that right there.
This is a great machine. You can buy one for about $5,000, and it's you know, you mill your own PCBs for it. It's awesome.
Well, that's cool. I'll have to look in that because it takes us a good 3 weeks to get any of our orders because they come from Germany.
Well, it's either done like in a couple hours.
Yeah, that's cool. I'll have to see if somebody will fund that maybe. I don't have that kind of money, but for my personal use, maybe someone will fund it for a research use. That's pretty cool.
All right, I think we're gonna let you go.
Okay, thank you for having me. I hope that was interesting and helpful.
No, thank you for doing this. And I'm actually interested. I was just thinking while I was here, because it's so fun to do it. But your takeaways and your challenges, we gotta have you back in like 5 years. And
See if they change.
then, yeah, why not? I'm sorry, we worked hard, but Dr. Rapson didn't make it today, so I'm afraid you had to experience a male-dominated audience.
Yeah, I couldn't see everyone. And I'm like, do I keep this? Do I just go click through it? Or
No,
and
you're good.
most people are great. Honestly, it's really a select few that are not. Like, I don't have a problem with anybody. I have people here that are very good about it, who are male as well. I don't think it necessarily matters, but there is sometimes a select few that I get.
No, it's important to bring up, and it's important for everyone to realize. And we were in a meeting the other day, and I had to wonder, am I talking over this person? Because I think I was, but so you need to be aware. So
Yeah.
anyhow,
And it's hard. You know, I was always quieter too. So sometimes I don't know if it's that or if it's,
well, you did say be curious, which you've always had, and then you put ask questions, and I went, huh?
less
Okay.
so.
Yeah. Yeah.
At least in a
So-
group setting, I less so ask questions.
Yep. Okay, thanks, Melissa. You really put a lot of work into this, and we appreciate it a lot. And it has an impact.
Okay, good. I'm glad. Okay, well, with that,
Take care.
yeah, have a good one, guys. Enjoy your night. Thanks for listening.
Thank you guys for being here. Okay. It's
That was awesome. You're always awesome.
she put a lot of work into that.
Oh, yeah, she definitely did. She did a great job too.
Yeah.
It's really cool. It's also funny, it's interesting what you were saying, or you were saying a minute ago, about, if you questioned whether you were talking over somebody or whatever.
Yeah.
The other day, I was writing, I had to do a letter of recommendation. And there was one of these questions, what are the first words that come to mind when you think of it?
Yeah.
And I didn't think, and I can't remember the words, but I started writing some words, and then I realized, oh my goodness, this is sexist. I probably wouldn't have come up with these words.
Yeah.
For a man, and I was like, oh, that's really very interesting, that I realized that I was actually had a gender bias.
Yeah. No, I think we were in that program review meeting, and it occurred to me a few seconds in, and I was the one doing the talking, that you may not have been there, but that it occurred to me that Valerie had been trying to say something, you know, and I was like, huh. And so I went, you know, and I stopped and I said, you know, Valerie's got a question, but then I thought about that for a while. I thought, geez, I think I was just.
Maybe you weren't though. You know,
Maybe
it's like-
not, but it's something to be aware of, because you can do it, I think, unconsciously.
Yeah, no, I think we do such things unconsciously.
Yeah.
And, it was funny that I caught myself too.
Yeah, no.
But of course, in her case, I found myself, I was trying to be kind.
No, I understand. I understand. Yeah, I know exactly what you're talking about, and I know the words too.
Yeah.
Yep.
Tomorrow, are you free to meet at 1 o'clock?
Perfect.
1 o'clock?
We'll do that.
Yeah, sounds good, because we'll be done with class by then, so we can just pop right in.
And I will try to have a completed draft with well, we're just you're gonna help me fill in some things. I think is the way it's gonna go.
Okay, sounds good.
All right, that was interesting.
Yes, yeah, definitely.
We can ask her what they were, but it certainly seems like, you know, they go in a little area and then.
Oh, yeah,
basically
so
just
what-
screw it right in. and see what
Exactly.
they have.
Mhm,
Yep,
mhm,
yep.
Yeah.
So, that would be cool.
Mhm.
Then you guys could work more on the back end than the front end, which is what would be, I think, more interesting.
Yeah. Okay.
End meeting for all.